All right, it is 1:35. I think we're still missing a couple people, but we will get started just because I don't want us to fall behind, and we have lots of questions to work on. So let's get going. So the first set of questions is on the amino acid structure lecture. This is just all the acids in case we forgot. Okay, so let's review amino acid structures. So I would like everyone to take a couple of minutes and draw the general structure of an amino acid. All right, does anybody want to volunteer with the trusty stylus and draw on the screen? No volunteers? All right, thank you. I promise it's not that scary. Go for it. It's a little laggy.
Okay. Okay.
Awesome, thank you. Cool. Did everybody's drawing look kind of like this one? Or I guess a better question is, did anyone's drawing look different from this one? So yeah, so most of the time when we see amino acids depicted, they're drawn like this, right, without charges. And this is what you'll see on the amino acid chart that I give you that is on Brightspace and that you'll see on your exams. But yeah, I talked a little about in the lecture how we don't actually see this form at physiological pH, right, or at any pH. Like in real life, you will never see an amino acid that looks quite like this with the charges like this. So does anybody have an idea of what I could change to make it more like what we might see in real life? Yeah. Yeah, exactly. So this drawing in red is a little bit more, say, realistic, but neither one is wrong. I just want to point that out. They're both accurate depictions if you just say draw an amino acid. But if you're talking about which one you would actually ever see, like in a beaker or in your body, it would be this one. And yeah, we'll get more into titrations and all that kind of stuff as we go through this lecture. So, any questions about amino acid structure? All right. So can somebody, or I guess take a minute and think about in asparagine, which is drawn here, where is the alpha carbon and where is the side chain? So does anybody want to tell me where the alpha carbon is on this molecule? Yeah.
The one with the H2 sticking out?
Yeah, exactly. Yeah, it's kind of hard to describe, but yes, this is the alpha carbon. Excellent. So it's part of the amino acid backbone. So the basic backbone of our amino acid has our amino group, which is here, our alpha carbon, which we just circled, and our carboxyl group. So that's the backbone. So where's the side chain? Yeah. Exactly, yeah. So everything that's not the backbone is the side chain. So that is over here. All right. Any questions about identifying the pieces of our amino acid? Okay. And a lot of times the side chain, we'll call it the R group. So now we have 4 amino acids that are drawn here. Yeah. Sure. Yeah.
Does the side chain, it counts as that carbon to the left, or does it count that bond attached to the alpha carbon too?
So, yeah, I would say the side chain kind of starts with this carbon here. This is, I mean, I guess you can't really count the bond as being either one. Yeah, it's not really a physical thing. Yeah, that's, yeah. Okay, so, all right, we have these 4 amino acids, isoleucine, glutamic acid, threonine, and lysine. And they are polar, nonpolar, positively charged, or negatively charged. So let's start with isoleucine, which is drawn here. So this is our isoleucine side chain. Is that polar, nonpolar, positively charged, negatively charged? Yeah. Yes, it is nonpolar. How do you know that? Yeah, exactly. So it's all hydrocarbons. And we consider carbon-hydrogen bonds to be, they are a little bit polar, but we classify them as nonpolar just for the purposes of biochemistry and most other chemistry. Yeah, so let's talk about glutamic acid. So glutamic acid side chain is over here. So what do we got for glutamic acid? Which type is it, A, B, C, or D?
Well, it's in physiological pH is negatively charged.
Yeah.
But you can also make an argument that it's polar because of the 2 oxygens.
Yes, yeah, I guess negatively charged is sort of a more extreme version of polar in that sense. But yeah, at physiological pH, most of the time, this will be this proton in the side chain will deprotonate from this carboxylic acid region, and we will end up with a negative charge. So it's acidic, loses a proton, or it donates a proton. So it's negative. So next we have threonine. So threonine, here is our side chain. Yeah.
Sorry.
Yeah.
So then how, for glutamic acid, why wouldn't you say it's polar then?
You could say it's polar. I guess it's yeah, I guess it depends on the pH. Since in the question I didn't specify the pH, yeah, if it's like a very, very low pH, like pH 1, it would not have lost the proton. So I guess you could call it polar. I mean, it's not that it's not polar. It's just that negatively charged is a more specific version. Like, yeah, you're right. The question isn't worded that great. Yeah, yeah. Or I guess maybe that would be, what is the best answer? And I guess the best answer is negatively charged, although polar is not wrong. Okay, so for threonine, which one? A, B, C, or D? Yeah, it is polar. What makes it polar? Yeah, exactly. So we have a hydroxyl group. Hydroxyl groups tend to make molecules polar. Oxygens are very electronegative, and hydrogens are not. You get some drawing of electrons, but yeah, it's not acidic. It's very hard to lose that proton. Okay, so our last one is lysine. So here's our lysine side chain. What would we have for lysine? Yeah, lysine will be positively charged. So that nitrogen, the lone pair, is basic. It gains a proton, so it is positively charged. Any questions about these classifications? Yeah.
In terms of length of that hydrocarbons in that molecule, would that be considered non-polar?
So, I mean, yeah, I guess you could say this region is nonpolar, but the side chain as a whole, because you would gain a proton here, would get a positive charge. Yeah.
So,
Yeah.
So, the OH group would always like overcome the methyl group, even like to make it polar, even though the methyl is like.
Yeah, so the methyl, yeah, like this area is kind of nonpolar, this area is kind of polar. Yeah, I guess you could make some arguments. I mean, here there's still few hydrocarbon character as compared to the hydroxyl group. I would say like it's pretty definitely polar. But if there was one that had, a very, very long hydrocarbon chain that had one hydroxyl, wow, sorry, my pen is going crazy. You could make an argument that that's sort of less polar. But for threonine in particular, it's hard to say that it's not polar.
So if there's one and one, we would always go with like polar.
Yeah. Any other questions? Yeah, and I guess to your point, there is some sort of wiggle room for like how different amino acid side chains are categorized. So there's the ones that the way I presented it in the lecture, that's sort of the way it is in the table on Brightspace. But a lot of times you'll even see later in one of the other chapters, there's a different picture that has different classifications for some of the amino acids. And so like I would usually say, cysteine is polar, but in this particular picture it said cysteine was non-polar because there's just a little wiggle room there because it has a sulfur, and sulfurs are a little less polar than oxygen, and so you could say it's not polar, but the edges are fuzzy, I guess. Yeah. Any other questions? All right. So all standard amino acids, and I'll emphasize standard, are which one of these?
I'll go with D, final answer.
D. Okay. Why do you say D?
I might be wrong. Because aren't all of them in like the? Oh, yeah. Okay. Yeah, it should be S. It should be because they're in the S configuration most of them, except for cysteine, right?
So yeah, it's true. You just got it. It's mostly, right? Not all. So this is sort of a tricky question. So you're right. Most of them are S, but not all. Because like you said, cysteine is in the R configuration. So it's not R or S. Any other ideas here? Yeah. Yeah. L. Okay. So why do you say L? Okay. Yeah. So we can go through that. So we also talked a little bit. I guess let's move. So we kind of eliminated R and S. So let's talk about dextrorotary and levorotary. So that refers to the way amino acids rotate light, or any molecule rotates light. And in the case of amino acids, it's about half and half. They're split. So some are levorotary, some are dextrorotary. But there's also this additional L and D nomenclature that doesn't refer to the way they rotate light. It refers to the configuration of the functional groups around the central atom. So the L, in this case, when we're talking about amino acids, refers to that configuration. So they're configured similarly to another molecule that I mentioned in the lecture. Does anyone remember what that molecule is? Yeah, so all standard amino acids are in the L configuration. So, I mean, they're configured just like a molecule that I mentioned in the lecture, and I was wondering if anybody remembered what molecule that was. I'm hearing whispers. So it's L-glyceraldehyde. I think I said it. It's possible I didn't, but I'm saying it now. So it's L-glyceraldehyde. And so the R and S also refers to configuration, but it has to do with the priority of all the different functional groups and things like that, and that does differ. They're mostly S, but one of them is R. But they're all configured the way L-glyceraldehyde is configured. So it's a little bit confusing because there's L and D, and they're not the same as levorotary and dextrorotary, but hopefully this helps a little bit. Any questions about this? Okay. Cysteine. Sorry, bad handwriting. Yeah. It could very well say lysine. Yeah. All right. So, how many chiral centers are in threonine? Everybody take a second and think about it. More than a second. I'll give you like 30 seconds. All right. So, how many chiral centers are in threonine? Go for it. 2. Yeah, where are they? Uh-huh. Yes. So, it is 2. Yeah. Yes, you could, because it's beta to the carboxylic acid. Yeah, so you could call this the beta carbon. Yeah, so that is threonine. Do most amino acids have 2 chiral centers? How many do most amino acids have? Yeah, just 1. Yeah. But some of them have 2, and threonine is one of them. Okay, any questions about chiral centers? So, more chiral center questions. What is the only amino acid that does not have a chiral center. I'm hearing whispers.
Easy final answer.
Yes, it is glycine.
Just that you got it right.
Well done, yeah. So glycine, on our alpha carbon, we have 2 hydrogens, right? Not chiral. All the other alpha carbons are chiral. Okay, another multiple choice. Which amino acid can form a disulfide bond? Yeah, cysteine. So cysteine has this sulfhydryl group on the end. It can lose a proton. It can stick together with another cysteine. So we can lose the protons, and then the sulfurs can come together and make a disulfide bond. And what kind of bonds are disulfide bonds? What? Yes, they are covalent. Excellent. So does anybody know or have a thought on why it's useful to be able to form disulfide bonds within a protein? Yeah.
It helps with shaping a protein. It creates the bands between the it helps with one. I don't remember.
Okay. Yeah. You have the right. Exactly. No, that's all you needed. So, yeah. So most of the interactions that are between amino acid side chains are relatively weak. A lot of van der Waals interactions, some dipole-dipole kind of interactions between polar ones, or dipole-induced dipole with polar and nonpolar. But covalent bonds, as we know, are very strong. So they can be really beneficial in helping a protein keep a very particular shape. It can bring together 2 different areas of a protein, glue them together in a relatively permanent way. Any questions about that? All right. So what type of amino acids can form a salt bridge? Yeah, B. Yeah, so positively charged and negatively charged. So a salt bridge is essentially ionic interactions, right? So positive and negative is a salt bridge. In general, salt bridges are not super duper common in proteins. You'll see them. More often you'll see those other weaker type of bonds like hydrogen bonds and van der Waals and all those other interactions. But you do occasionally see a salt bridge, and salt bridges are fairly strong because they are ionic interactions. They're sort of on the level of covalent bonds, as we talked about in our very early lectures.
Question: would they kind of denature in like a ionic solution or in a aqueous solution?
Yeah, so they're in an aqueous solution, especially probably depending on the pH of the solution. You can easily break the salt bridges. So, in particular, covalent bonds would be a stronger bond in this circumstance for sure. Yeah. Yep. All right. So, which of these amino acids constrains the conformation of a polypeptide chain? So the conformation refers to the shape, essentially, or the configuration of all the different groups. And constrain means it stops it from free movement, essentially. Yeah. Yeah, exactly. So if we think about our sort of typical amino acid, so let's look at valine over here because it's drawn already. So when you have your alpha carbon here, all of the groups attached to it are able to freely rotate around these bonds, right? These can all rotate, these can all rotate. So if that's in, you know, a polypeptide chain, you can have a lot of rotation, a lot of freedom of movement. Everything can kind of move around how it likes. Proline has a problem, right? Because around this alpha carbon, now we have this ring structure that formed. So these bonds can't really rotate quite as much as they would want to. This bond can still rotate. Whoops. But those ones are kind of stuck in the ring. And so everything attached, on, especially on this side, is kind of a little more stuck. Any questions about that? All right. So that brings us to our amino acid reactions questions. So, oops, I did not remove this. Okay. So let's review our amino acid reactions. So, how many, I guess everyone take a couple minutes and take a look at this one, talking about amino acid ionization. All right, so how many, first blank, amino acids have how many ionizable groups?
2.
2 is a good answer. Are there any other numbers that you could put in here? Yeah. Yeah, some have 3. So you could say 2 to 3. It's usually 2, that's true, but it's sometimes 3. Can anybody tell me what is an ionizable group? Yeah. Exactly, yeah. So ionizable groups, that's referring to the gain or loss of protons. All right, next blank. At a pH below its pKa, is a group protonated or deprotonated? Protonated, yeah. So here's a thinking question. If a group is protonated, does that tell you what charge it has? I'm seeing some confusion and also some shaking no. And yeah, that's right, no. So just because something, so some groups when they're protonated, they get a positive charge, like an amino group, right? So they'll go from NH2 to NH3+. But some groups when they're protonated, that doesn't happen, right? So think of a carboxyl group. When it's protonated, it goes from a negative charge to a neutral charge. So when we're considering pHs and pKas and getting protonated and deprotonated, we also have to think about what that means for that particular functional group, like what its actual charge might be. It could be negative, positive, or neutral. So, last question. The alpha amino group has a pK of approximately what? Yeah. Yeah, 10-ish. And the alpha carboxyl group has a pK of approximately, yeah, I'm seeing some 2s. Excellent. So, Yeah, so you should know these in general. Know that alpha aminos are about 10, sometimes 9, sometimes 10. Carboxyls are pretty close to 2. You don't need to, memorize for any specific amino acids what those specific numbers are, but just know these kind of ballpark numbers. Any questions about amino acid ionization? All right. So let's squeeze in one more question. Or maybe let's, how about everyone start thinking about this, but maybe we'll discuss it next time just because we're running low. So I'll give everybody like 3 minutes to look at this. Yeah, so quiz 4 is due 1 week from today. We will finish chapter 4 on Monday, so then you'll have between Monday and Thursday to do the quiz. Yeah. Yeah, and quiz 3 is due Monday. Yeah. So, does anybody want to tell me what the charge would be at pH 7? Yes, -1. And yeah, do you want to tell me how you need that?
So pH is 7, the two carboxyl groups will be negative.
Mm-hmm.
And then the ally group stays positive.
Yeah, exactly. So for our carboxyl group, our first pK is 1.99. pH 7 is above that, so we're going to be deprotonated. C's OO minus. Same thing for our side chain. The pKr is 3.9. pH 7 is above that. We're deprotonated, so we're COO minus. And for our amino group, the pK is 9.9. pH 7 is below that, so we're protonated. So our amino group is positively charged. Add together those charges, you get -1. So can anybody tell me what our charge would be at pH 12? Yeah. -2. Yeah, and why is that? Yeah, we're still above these. Exactly. Yeah, so pH 12, now we're above the pK for the amino group. We are deprotonated, so we are in the NH2 form. We have 2 negatives and a neutral, and that adds up to -2. So as a a bonus thought. Can anybody tell me a pH at which this would be a Zwitter ion with a net charge that is neutral or no net charge? And I know it's time, so why don't we think about that and we'll pick up there on whatever day, Monday. Yeah. So it would not be 5, but keep thinking. Yeah. Yeah, if anyone has questions, I have office hours after this, and I'll leave you in suspense until Monday. It would be 3, yeah. Suspense over.